So, good day students, and welcome to the second nugget in the lesson dealing with biofuels. Today we will talk about pellets, briquettes, pulverized fuel and other fuels that have been produced only through changes of the physical properties of the raw material. So what we are dealing with now are changes in density and in diameter. I will concentrate on wood-based fuels, but I will mention also some other types of biomasses. You will find these things treated in the Busy Plan Handbook, section 412F. When it comes to the preparation of wood prior to physical upgrading, is the most important thing to arrive at the correct moisture content. You are probably well aware that soaking wet wood is almost rubber-like to its behavior. It's very tensile and elastic. In contrast is completely dry wood, very hard and very brittle. So you will realize that the mechanical properties of wood change very much with the moisture content. So before you attempt to grind or compress wood, you want to set the moisture content at the right level. There can be multiple reasons to change the physical properties of the material. A density increase, compaction, pelletisation or briquetting will increase the energy density. In case the subsequent transport is volume limited, will this improve transport economy. But if there is no transport following, or if the transport is weight limited, then this will not change the expenses. Compaction is in itself a reduction of porosity and may improve the hydrophobic properties of the material and make it less sensitive to moisture and damp air. This may also improve its resistance to microbiological attacks. The uniformity of the particles obtained by these processes will improve the precision when it comes to feeding and dosing with the end user. Milling the material into a fine powder will generally reduce the bulk density and hence the energy density. In most cases will the bulk density become so low that transport economy is seriously affected. Milling will also increase the external particle area in square meters per kilo and may, because of this, be an invitation to fungi and bacteria to attack. For the same reason, the increase in external area can the combustion intensity with the end user be increased. These two, compaction or milling, will be the main methods for physical processing. Let us now look at compaction from a money point of view, but without any money involved. In the previous slide, I mentioned that compaction to a uniform particle size will have an influence on the control system with the end user. Not only that, with wood pellets, look at picture 414 in the Busy Plan Handbook, you will notice that the outer surface of the pellets is blank and smooth. Compare that to the chips shown in figure 118. You will realize that the pellets are much simpler to feed into the burner or into the boiler than the chips. Chips tend to stick to each other, clog, form bridges, and on the whole cause a lot of problems in the feeding. So pellet feeding requires only a very much simpler and cheaper equipment than chips feeding. But then, on the other hand, will the pellets be much more expensive than the chips? The slope of the two lines in the diagram is proportional to the specific expense per energy unit paid for the chips and for the pellets. So what you see from this is that to the left of the dashed line will pellet firing be cheaper than chips firing on a whole year basis. So there is a natural market for wood pellets to supply smaller scale energy plants. The small scale extends from air heating stoves in household scale to summer load hot water boilers aimed for shopping centra, hospitals or alike. At least this is so in Sweden. In your country may the situation be different. Wood briquettes are less mechanically strong than pellets and tend to break during transport, loading, reloading and feeding. Because of that, will the expense for feeding and dosing equipment be in between that for chips and that for pellets. The pressure in briquetting is much less than that for pelletizing, so the wear of the equipment is much less, and the specific costs for briquettes tend to fall between that of chips and that of pellets. When it comes to grinding and producing a fine powder for pulverized fuel firing, does the distribution of expenses become much more complicated. Pulverized fuel firing is indicated by the green line. Provided the transport cost and the milling can be kept low, may the specific cost be kept under control. The milling energy is one important part of the pulverized fuel cost. To reduce the milling energy, it may be a good thing to torrefy the material. The most common in Sweden is that plants using wood powder as a fuel tend to buy wood pellets, and then they have their own mills to grind the pellets into powder. Being large, can these plants negotiate a good price for the pellets? And the transport cost becomes low because it is pellets. And since the pellets are uniform, will the feeding and the milling be relatively cheap? So in these cases, are the pellets just a transport packaging? Burners are expensive, and so are panel wall boilers. So the starting point on the y-axis is high. But if the combustion intensity can be raised to high values, then may the boiler volume be kept relatively small, and that contributes to limit the initial cost. As you will see, may pulverized fuel firing be competitive to the right of the dotted line, if the expense per energy unit can be marginally kept below that for chips, and that can only be obtained if the volumes are large and the contracts signed are long-term. So unless you have residual wood powder like grinding dust available from, say, a nearby carpentry, it will be a fuel only to be used in the large scales, like 100 megawatt or larger. Again, this is the situation in Sweden. But let us now look at pelletisation. In the Busy Plan Handbook, Chapter 4.1, is pelletisation mentioned in several places. More specific, you may want to read section 4.1.2f. You may also want to download the paper Fundamentals of Pelletisation by Henriksen and co-authors. The paper is from 2008, but I still want to recommend it because it treats not only wood pellets, but also straw pellets. One major difference between these materials is that straw pellets, for mechanical strength, need a binder, and this is treated in the paper. There is also a summary of which federal European standards are valid for fuel pellets. So this paper is fairly comprehensive. But let us now have a brief and simplified view on what pelletizing is and how it works. The animation in the slide illustrates how pelletization happens and how a pellet mill works. The channels through the ring die consist of a conical inlet section, a cylindrical section and a conical outlet section. The compression mainly takes place in the conical inlet. This compression is two parts. There is an elastic deformation. This is a deformation that disappears when the pressure is removed. Like if you have a balloon in your hand and you put pressure to it. When you remove the pressure, will the balloon take its original shape again? And then there is a plastic deformation. This is a deformation that remains once the pressure is removed. But the plastic deformation is not finished in the inlet section, and it has to be fixed. In the cylindrical section is the material held back by friction to the walls, and then the pressure inside the pellets becomes very high. At this high pressure will the cell walls in the wood break, and the temperature raises to well above 100 degrees Celsius. What happens then is that the lignin in the wood becomes soft and sticky. So the lignin penetrates the broken cell wall structure and glues the broken bits and pieces together into a new and compacted structure. You will find this described a bit in the paper by Henriksen and co-authors, section 6. The process needs a certain time, so the length to diameter ratio in the cylindrical section are very important to the mechanical durability and properties of the pellets. On escaping from the die are the pellets some 100 to 120 degrees, and they are soft. So they then need to cool slowly to become the rigid and sturdy product desired. Section 8 in the paper by Henriksen and co-authors will give you examples of standards and quality criteria for pellets. The final pellets typically have a solid density about 1100 kilos per cubic meter, and that yields a bulk density about 700 to 800 kilos per cubic meter. The theoretical maximum for the solid density of the pellets is 15 to 1600 kilos per cubic meter. That is the solid density of the cell wall itself. But going to that density would require even higher internal pressures than the 700 bars usually applied, and the wear of the die would become too high. So some 1100 kilos per cubic meter is a reasonable compromise. What I said in the previous slide about lignin being the main binder is according to the most widespread theory today. However, other substances like polysaccharides and fatty acids may also play a significant role. Nevertheless, generally speaking, it is more difficult to produce durable pellets from materials that have a low lignin content. Such materials are, for example, herbaceous biomass like straw and sorted organic waste fractions. The paper by Whittaker and Shield mentions a number of different possible binders and additives that may be used to improve the mechanical durability of pellets made from herbaceous biomass. The paper can be found at Science Direct, and you will find a link among the external links to this nugget. But also other materials, such as sorted waste fractions, are interesting for pelletisation. The fuels from such processing are generally called RDF, for refuse-derived fuels, and may contain clean fractions of waste. Such fractions will be unpredictable to composition and may pose great problems in the pelletizing process. One paper dealing with this problem is written by two Thai researchers. I do not dare to try to pronouncing their names, but you find their names and the paper title in the slide. The paper is available from ResearchGate, and you find the link among the external links to this nugget. You will notice that the experiments referred in the paper include plastic fractions in the RDF. This is quite common and obviously disqualifies the RDF in this study as a biofuel. But there is nothing to say that RDF could not be pure biomass. This is a question of how the waste handling system is organized, so it's a purely administrative thing. In section 2.2 of the paper, it is mentioned that the briquettes had an inner diameter of 1 centimeter and an outer diameter of 5 centimeter. This indicates that the extrusion process used a screw extruder. The video illustrates the function of a screw extruder. Another common type of equipment used for briquetting is the excenter press. Screw extruders may give high pressures and compact products. Excenter presses are cheaper but cannot give as high pressures, so the products will be less durable. Among the links to this nugget you will also find one link to a briquette film. That was recorded some years ago during a student visit, but it might give you an idea of how briquette production looks in the large scale. Now read the papers I have recommended before you go on to the homework session.